Today is the 22nd of April, 2024. So, we are continuing discussion and investigation of effect of neutrino spin flavor mixing and oscillations engendered by the big interactions of neutrinos with the matter in the case when there is no trivial, not zero, transversal component of the current. This is a new phenomenon that we are now examining, studying, and discussing. And we have derived in our previous lectures the evolution Hamiltonian for two neutrino mass states, case, two neutrino flavor states, plus two spin states. So we consider the neutrino state in the following way. So there was electron left, electron right, muon left, and muon right neutrinos. So, and we derive a complete evolution Hamiltonian in the case of presence of magnetic field with the longitudinal in respect to neutrino propagation and transversal in respect to neutrino propagation components, plus we consider the current of neutrons, matter composed of neutrons, and this is a kind of a model of a neutron star, yeah, which is composed of mostly of neutrons. About 80% of particles in the neutron star are neutrons. The rest 10 are electrons and protons. So, in equal amount, yeah. And we consider this current to be composed of two components, longitudinal and transversal in respect to neutrino propagation. And we derive the full Hamiltonian accounting for both two phenomena. Electromagnetic interaction of neutrinos with the external magnetic field due to non-trivial magnetic moment, plus weak interactions of neutrinos with neutrons from the moving matter. And then we decided to consider the evolution of a system of neutrinos composed of left and right electron neutrinos. And we were studying neutrino mixing and oscillations. Between these states, so electron left oscillate, we just use this notation, in the presence of transversal current and transversal magnetic field, oscillates to neutrino right state. So here we just only indicate two guys which result in transition between different spin states. Yeah? Of course, we also account for longitudinal current and longitudinal magnetic field. But here we just write that this is particular source of this transition, this change of spin orientation of our electron neutrino. And just the final expression that we have derived. So for this, we consider 2 by 2 oscillations. There's two neutrinos, and the evolution equation that we have derived last time has the following form. I will not repeat all notations because then we shall use it. Our next step, we shall write resonance amplification condition for these transitions. And then probably maybe one of the first time I will put real numbers to understand whether this effect can be observed somewhere and somehow, just to have some feelings among the fingers, yeah, just to understand what kind of effects are expected in nature, yeah? On this particular very simple example. In our paper published with my student, postgraduate student Pavel Pustoshny in PhysRevD in 2018, we considered different other options, different other transitions. So we also considered, for instance, the transition between different flavor states, yeah? Also, transition with the change of spin orientation, also with change of flavor. Obviously, this is spin flavor oscillations, yeah? And this is spin oscillations. And some other cases, yeah? Also, we include the effect of longitudinal motion of matter and longitudinal magnetic field. That, as you can see from the complete evolution Hamiltonian, enters the diagonal terms in the evolution Hamiltonian. So it means that longitudinal magnetic field and longitudinal current can violate or produce or annihilate the resonance condition, you understand, yeah? Because they enter the diagonal elements of the evolution Hamiltonian. And they cannot change the spin orientation. The spin orientation is changed only due to electromagnetic or weak interactions with transversal magnetic field and transversal current, okay? So, and for this particular case we are discussing and examining, we have the following evolution equation, I d over dt. Our state, this is electron left or electron right. And here is 2 by 2 Hamiltonian. This is a part of our 4 by 4 Hamiltonian we derived. The first term in first line is mu gamma EE, B transversal longitudinal, plus eta EE, that is equal really to 1, but I just put it in order to reflect the correspondence with the case of magnetic field only presence, yeah? Well, this is the Fermi coupling divided by square root of 2, the density of neutrons of our matter minus, this is the V beta is the speed of neutrino. The modulus is very, very close to 1, yeah, because we are considering dealing with the relativistic neutrinos. And this is V is the velocity of matter, yeah, the vector velocity of matter. So this is the first term in the first line. This is the second term, this effective magnetic moment of electron neutrino. If you remember, if you just introduce electromagnetic properties for the mass states of neutrinos via mu11, mu22, mu12. This is a combination of these fundamental magnetic moments introduced, diagonal and off-diagonal, introduced for the mass states. Each of these moments introduced and determined in the mass states are multiplied by some function of mixing angle, cosine theta, sine theta, etc. Yeah, okay. Multiply by the transversal magnetic field plus E to gamma EE. Again, this is the Fermi constant and the density of neutrons multiplied by the transversal speed of our matter composed of neutrons. So here I put electron left, electron right, and the second line of this effective Hamiltonian, evolution Hamiltonian. Okay. Again, mu EE B transversal plus mu gamma EE Fermi constant waved density of matter V transversal. And here we have the second term in the second line, the second column, mu divided by gamma. But this is really not any deviation, but this is a value, yeah? It's not a ratio between some mu and gamma. You remember, yeah? You put such a notation. Multiplied by the longitudinal magnetic field minus, again, E to EE, Fermi coupling, and multiply by 1 minus vector V, vector beta. So that's what we have. So let's put here what is mu EE, where? I just put here, where? Mu E effective magnetic moment of the flavor electron neutrino is fundamental magnetic moment of the mass state 1 neutrino cosine double theta plus mu 22 sine cosine double theta. Probably I just use mu1 and mu2. I don't remember because there was no sense to write mu11. It is enough to write magnetic moment of the first mass state of neutrino of the first mass state, yeah? And plus mu12 is transition magnetic moment in the basis of the mass states neutrinos. When the magnetic field is applied, due to this magnetic transition, if it is not zero, it can be not zero in theories beyond the standard model. Of course, but obviously, if we are speaking about magnetic moment not zero, we should be beyond the standard model, because in the standard model, as you remember, the mass is zero, and it's very hard to generate non-trivial magnetic moment for the case of if mass is zero. Yeah, and this is a transition magnetic moment. This is next step beyond the standard model. So not only just introduce the mass states that produced by polarization, vacuum polarization loops, effective magnetic moments in the mass states proportional to, in the case of Dirac neutrinos, proportional to the masses of the mass states of neutrinos, but we also suppose that probably in some more tricky generalization of the standard model, also a transition between different mass states with different spin orientation can be produced by transition magnetic moment interaction with the transversal magnetic field. And this is mu1, 2 multiplied by sine double theta. Yeah? This is one guy here, unknown, let's say. And this is another one. I just write eta EE equal to 1. I'm sorry that I always just write it, but historically it is always in our formulas, and I just continue to reproduce one in such a strange way. Yeah, because, as I have told, formulas become very symmetric formally. If you consider separately the case of only matter current presence or magnetic field display, they are very similar. But in the case of interaction with matter current, weak interaction, this E should be equal to 1. Yeah? Okay, and what else? This guy, EE. This is cosine double theta divided by but here I will not write 1, 1. This is gamma factor for the mass state 1 neutrino, yeah? Okay. Plus sine double, not double, I'm sorry. This is, should be squared, yeah? Should be squared, yeah? Yeah, okay. Cosine squared theta sine squared theta divided by gamma of the second mass state, neutrino, yeah? So all guys are just now expressed exactly, and gamma I equal to the energy of I type of neutrino divided by the mass, yeah, of neutrino. So and now we would like to study the possibility for the resonance amplification of these transitions and oscillations between different mass states of neutrinos of the same flavor, electron flavor, we have chosen it. So the question is when this transition or transition between these states would become important and feasible. Yeah? So we would like to put real numbers and see when it can be expected to be realized in nature. Yeah? So I just put this like this. So the probability of oscillations can be derived in a very similar way as we have done it when we considered the flavor oscillations, the probability of flavor oscillations in magnetic field, or accounting in addition magnetic field plus matter at rest. So this probability of oscillations as a function of distance that neutrino has traveled equals to E squared effective. I just divided by E squared effective plus some delta effective squared also, where multiplied by the term that is varying as the sine squared with the distance x, yeah, where this E effective equals to the modulus of effective magnetic moment of electron neutrino multiplied by, this is a vector, multiplied by the transversal magnetic field, eta divided by gamma EE, G Fermi, and density, and this is the vector of transversal current of matter. Yeah, this is modulus. And delta, correspondingly, equals to, again, modulus of sum of two vectors, mu gamma EE, B longitudinal, this is a vector, in the direction of neutrino propagation, multiply by 1. I don't want to write this eta EE, Gn 1 minus the product of two vectors, the speed of matter and the speed of neutrino, multiply by the vector of speed of neutrino. This is the longitudinal magnetic field, and this is longitudinal current of matter, because it is orientated along neutrino propagation. So, when the transition between these two states are important. Obviously, when the amplitude of oscillations is not very small, the maximum value can be 1, yeah? If you just, in the denominator, we just add something positive to numerator, yeah? The maximum value is 1. It means that the most important case realized when delta tends to 0. But if not, if, let's put a criteria, when this guy, I mean the amplitude exceed 1/2, let's say, let's put, or 10%, as you wish. But I suppose to put a criteria that it is important criterion. So when effective bigger than delta effective, okay? So it means that we just put a criteria that the amplitude of oscillation equal to 1/2 or exceeded. Yeah, this is more reasonable, more democratic, I should say, criteria. Yeah? Of course, you can put 1% or 10%, depending on your wish. And a real situation, probably you might be interested to consider incorporated effect. But if you just put very reasonable, so this guy is bigger. The amplitude of oscillation is bigger than 1/2. Okay. And let's solve this equation. Yes, let's solve the equation so E effective equal to delta effective. Yeah. So and first let's simplify the problem. The task, let's say. Not the problem, but problem can be simplified. The task can be simplified. Yeah? Okay. And first we consider the case when the magnetic field contribution is negligible. So we are interested, because we have studied before the neutrino mixing and oscillation in longitudinal and transversal magnetic fields. Now we are particularly interested in the effect of neutrino interaction with the moving media. So let's switch off or just neglect the effect neglect the effect of magnetic field. Then, from these two formulas above, we get that E effective equals to modulus eta gamma EE, Fermi coupling waved, V, the density of matter and the transversal magnetic speed of matter. And E effective equals to modulus, again, this G wave, n 1 minus the product of two vectors, the speed of neutrino and the speed of matter. And this is nearly unit by modulus vector in direction of neutrino propagation, yeah? And the oscillation length, I haven't introduced here the oscillation length. The oscillation length just have very simple expression in terms of this E and delta equals to pi divided by square root. The square root, yeah, of sum of squares of E effective squared plus delta effective squared, square root, yeah? This is the general definition for the oscillation length. And if we just consider the case when magnetic field is switched off, yeah, or out, I don't know, then this oscillation length, this is important for the further estimations, is pi divided by this E, modulus of this E. You just write eta gamma EE, coupling waved constant, and the modulus of transversal velocity or speed of matter, yeah? I just recalled that G wave equals to, I was not correct saying by square root divided by square root of 2, but divided by 2 and square root of 2, yeah? I just make this mistake when I was saying about this constant G waved. So now let's apply this condition. Let's call it the resonance condition, or just the condition under which neutrino mixing of considered type and the corresponding oscillation become important. Yeah? Well, let's apply this and just write following two realistic expressions for this delta effective and E effective. So we get that the condition is as follows. This is eta gamma EE V transversal modulus not less than 1 minus y. Because, well, I suppose that do you agree with me? Okay.
Maybe multiply it by
Huh?
beta.
Beta, yeah, of course. Beta is equal to 1. Do you agree with me? Oh, of course, less than 1. This is speed of neutrino. We consider relativistic neutrinos. Okay, of course it is less for relativistic neutrinos. Yeah? Okay. Now let's make some manipulations. Let us consider this term. So, suppose that delta m, that is in our case the mass difference of two considered mass states of neutrinos, is much less than m1 and m2. Let's consider this particular case, that the difference of the mass is much less than the absolute values. Huh? Why not? Then we can write that introduce some general new neutrino that is something like inverse gamma for the first mass state of neutrino, and that is about the same order that the second mass state gamma, yeah? If the difference is very small, yeah? Okay? But neutrinos are relativistic, so all these gammas are much greater than 1, because the energies of neutrinos reasonably increase their masses, yeah? Okay? Then we can simplify if you just use the exact expression for this. We can write, if you remember, I just remember, cosine theta divided by gamma 1 plus sine squared theta divided by gamma 2. That is something like this new gamma, yeah? Okay? Do you agree with me? Sine squared theta plus sine, cosine squared theta equal to 1, as we know for many years, yeah? From our childhood, eh? Okay? Then we have derived in a more simple way this term. So what we can write? We can write this modulus of transversal matter speed divided by this universal gamma for neutrino, determined in this case, yeah, should be not less than 1 minus v beta, yeah? This is the condition. This is a resonant condition, as we call it. When this condition is fulfilled, the amplitude of oscillations about 1/2 or even bigger, yeah? Now let's go further and just make some more exercises about this. So this term this particular, is this 1 divided by gamma nu is bigger than V transversal divided by gamma nu, okay? Because the speed in any case is less than 1, yeah? Okay, this is bigger, okay? If we just close this and change this by 1, yeah? We put its bigger value. So it means that this condition remains valid. So we can write a more simplified condition that this condition should be fulfilled, yeah? Okay? Now, this value is much smaller than 1. So it means, and this is bigger than this, yeah? It means that 1 minus V beta should be much less than 1. You agree? It cannot be equal to 1 or to 2, because the maximum value can be 2 if these two vectors are oriented in opposite direction. B is per modulus about 1. Relativistic motion of matter also, let's suppose, maximum value it could be a little bit less than 2, yeah, okay? So, but this is value that exceed this, but it's very, very small. It means that this guy should be very, very small in any case. And when it happens? When 1 minus something very close to 1. You agree? So it means that the cosine between these two vectors are fixed to be positive, yeah? So, what we can say? It means that in order to this resonance condition to be valid, in our case, this is important, we suppose that the distribution between values of masses are very, very small, small in respect to the value of absolute values of masses. So it means the cosine theta between these two vectors, between vector, please don't mix it with the mixing angle. This is a vector between theta between two vectors, yeah? This is theta, nu beta, yeah? It should be positive, yeah? Then we can go further. I just put here plus, and we get the following. We get the following, that 1 minus V vectors, that is minus modulus of these vectors, I just stress it, cosine theta, should be bigger or equal to 1 minus V modulus, if cosine is positive, yeah? So we extract something a little bit smaller than modulus of two vectors, we extract from 1. It means that this guy is bigger than this one, for sure, yeah? Because of positive value of the cosine theta, yeah? Okay? Okay. So, in order to a resonance condition to be fulfilled, for sure it should be, for sure, it should be the following. 1 divided by gamma of these neutrinos, 1 minus modulus of two vectors. So, this value is very, very small. And by the way, this is what it is. It can be written approximately 1 minus V longitudinal. And if very, very small value is bigger than 1 minus something, it means that V is about 1 and V transversal is much less than V longitudinal. Huh? You agree? So now we have some feeling when this kind of transition engaged by the weak interactions of neutrinos, electron neutrinos, with the transversal matter current can be important. This is not very good condition, by the way, because this guy determined, if you remember, in the denominator, the effective oscillation length. Do you remember that effective oscillation length in this case yeah, is inverse proportional to this transversal, it is very similar for the case of magnetic field. Yeah, effective is proportional to magnetic field. Yeah, transition magnetic field. Very similar. Yeah? So it means if this is very small, it means very huge scale of matter moving with non-zero reasonably small, but nevertheless with non-zero transversal speed should exist. So it means that the scale, the dimension of space where this effect can be realized become rather wide. It's not good, yeah, because it will be much better if the all happens in a very local dimension space, yeah. But nevertheless, let's try to estimate what is the scale. Yeah, let's go further. This is like curiosity. So what else? What we shall do else? So I would like to discuss more this. How it can be treated. This is 1 minus the modulus of the vector of speed of matter and the vector of velocity, velocity of neutrinos. Yeah, we expand it, and we just write that this is 1 minus. There are two vectors, and we introduce. Let's say I just introduce right here. So. I just recall you the following notation. So the gamma for the particles of which matter is composed, the gamma, yeah, is related to the speed of matter according to this expression, yeah. So then we can write that, but it's obviously known. V is the speed of neutrons, yeah, as a whole, yeah, the speed of matter. So this V equals to 1 minus 1 divided by squared gamma neutrons, square root, and taking into account that this gamma is very big, we can expand and just extract only two terms, the first and the second one. And it reads that this is 1 minus 1/2 divided by gamma of matters of which particles are composed, matter is composed, plus much smaller values. And identically we can write for a neutrino speed beta equals the same, 1 minus 1 divided by 2, and in the denominator the gamma neutrino squared plus extra very small terms. And now let's include all this to this relation and just take care about the most important contributions in the expansion of these two velocities or speeds, the speed of neutrinos and the speed of matter, accounting for the case that it is a relativistic object, yeah? Objects. So we can write that this is minus 1 half 1 divided by square of n plus multiplied, this is the one speed, the second speed, the same 1 minus 1 half 1 divided by gamma neutrino plus not important terms, and this is approximately, if I just neglect not important term, 1 half 1 divided by gamma n squared plus 1 divided by gamma neutrino squared. And now it is reasonable to expect or consider that neutrino is more relativistic than matter, yeah? Because neutrino is moving much faster, I should say. The speed is much closer to the speed of light than the speed of the general average speed of medium. Yeah, it's very hard to imagine that the huge macroscopic amount of matter is moving with a very high speed, so just exceeding the gamma for this motion, exceeding the gamma for neutrinos. So here we consider that neutrinos much bigger than gamma that describes the motion of macroscopic motion of external environment matter. Yeah. So then we can say that this is approximately in this. So in other words, we consider that neutrino is more relativistic than neutrons of matter. Yeah. Understand? Yeah. So it is equal to 1 half divided by gamma n squared. Yeah. So if you agree, we can go further. I can switch. Yeah. Okay. To the next. Then we can get that the resonance condition. Then let's say the resonance condition for the transition, I just recall. Sorry. Under the influence of transversal matter current, now reduces to the following. So it was like this. I just write it once again. So, and it's now reduced to 1 divided by nu gamma nu exceed 1 half 1 divided by gamma of matter. Yeah. So then we just obtain that this should be like this. So this is most simple and most transparent, I should say, condition. So when this condition is valid, then the amplitude of oscillations between electron left and electron-right neutrinos produced, a mixing between these states produced by weak interactions of neutrinos with moving matter, accounting longitudinal and transversal components, exceed 1/2, yeah? Exceed 1/2. Now consider the case for example, the case when M1 and M2 equals to something like O1 EV. Let's consider this case, yeah? And the energy of neutrino equals to 10 MeV. Then this condition, these two conditions, are valid for ultra-relativistic background matter with gamma exceeding gamma nu 1/2, that is 3×10⁻³ And the question is, what is the effective oscillation length for this case? That is equal, I just recall, pi divided by eta gamma EE, wave complete constant, n, yeah? What this value is? I just probably here I should write this, okay? I just missed this. If to go further, we can write that effective length in this case equals to pi divided by, again, eta divided gamma, the coupling, 1 divided by gamma n equals to pi gamma n divided by eta gamma EE g-waved n. I just would like to recall that this is 2 divided by gamma neutrinos. Yeah? And then we have to make these estimations. I would like to supply these further estimations by the following very important numerical estimation that is useful in any case when you are considering the effect of neutrino interactions with different particles of the environment. So the key point is this Fermi coupling multiplied by the number density of matter, and let's take some reference value for this combination, the Fermi coupling and some fixed density of matter, fixed value. So consider, and then we use this estimation in any further estimations. So n, let's call it n0 reference number, the Fermi coupling without square root of 2 and 2 in the denominator, a real coupling. So, and let's consider the particular case of quite dense matter, 10 to 33 centimeters cube inverted. Yeah? That's like a reference value, and then we use it for our estimations that we have now interrupted, but then in further estimations. So this is 1033 centimeter minus 3, and if you remember, you can look in some website, or this is 10 to minus 5, 1 GeV squared. This is what the Fermi coupling is, 10 to minus 5 divided by more or less the mass of the proton or a neutron squared. This is what is important. The Fermi coupling is inverted, is proportional inverted to mass inverted mass squared, obviously, because if you remember, this comes from the propagator, yeah, of the vector boson. There is in the non-relativistic case, in respect to energies, respect to the masses of the boson, it reduced to a factor of mass inverted mass of the boson. Yeah, so mass squared in the denominator, and then here we just use the following, that 1 centimeter inverted in the system where C and H equal to 1, we just make all these calculations, and speed of light and this H bar is equal to 1. This is 2 multiplied by 10 minus 5 eV. So centimeters are related to in this system, CH equal to 1, according to this number. So it means that 1 EV equals to 1 divided by 2 multiplied by minus 5 centimeters. So this is the relation between electrovolts and centimeters. Yeah. So the speed of light and Planck constant. Yeah. So now put all these numbers here. So this is 10 to 33. Then we just put these centimeters cube in the denominator. This is 10 minus 5, this one. Then 2 in the denominator, in the third, it will be 8 multiplied by 10 minus 15 electron volt cube divided by 10 to 18 electron volt squared equals to, if you just calculate all these numbers, it equals to 8 multiply to 10 minus 5 EV equals 4 divided to centimeter. This is the value of reference number of density 1033 to cubic centimeter multiplied by the Faraday coupling. Yeah? If you just use this, and if you return back to the interrupted estimation for the effective length, okay, the effective length after all these estimations, we get the following, that the oscillation length, I would like to ask you to check this estimation, equals to more or less reasonable value of 50 kilometers for n equals to 10 to 37. When gamma equals 3, 10 to the third. So this is the answer. So I just a little bit increased the density of matter in respect to what was supposed initially, yeah, in order to have not 1,000 kilometers for estimation for the oscillation length. Yeah? So 50 kilometers, it's more or less the scale of the neutron star. Neutron star is 10 kilometers, but if you just look in the very first moments, the matter is spread in a wider range, so it means that this is more or less of the scale. Yeah, you understand that in order to have the amplitude of oscillations between left and right electron neutrinos engaged by the interaction with transversal matter current, you should a huge density of this current, the huge density, the huge gamma factor of this extremely relativistic moving matter, and, well, not huge, but rather big scale where this effect should proceed. Yeah? So it means that these conditions should be more or less valid on the dimension of about several tens of kilometers. So it means that really it's not so easy to find probably a realistic situation in astrophysics when this effect can take place. But we have considered only one particular case, only one particular example of transitions between different spin neutrino states, and we consider neutrino transition with change of spin orientation without change of flavor. Yeah? So I would say that if we shall do this next time, we estimate the transitions between different flavor states with change of spin. And now, and then it will be possible to find a realistic situation when in examining a realistic model of the gamma ray burst, yeah, it is possible to expect that this effect can take place there.